Hello class, today we're going to be learning lesson 4-6 in our algebra book. The title of it is Fit a Line to Data. And what this is talking about is that in real life, if we're going to take a sample data and we are going to plot it, probably a majority of the time it's not going to fall on a straight line. You might have scattered data. And when you see this, it's called a scattered plot. Alright, so we might have data that looks like this. Right? It doesn't necessarily look like it's on a straight line, but I can kind of see the relationship between the points. That down here, when the y is lower, so is the x, and as the x gets bigger, the y increases as well. When this happens, it's going to be called a positive correlation. So I'm just going to draw a red line so you can kind of see, yeah, it looks like a line that would have a positive slope if all those points were surrounding that line. So we're going to call this it having a positive correlation. And what that means is that all of the data has a positive relationship. Okay, so if y is increasing, x is increasing as well. You might come across other graphs that tend to have their points going downward. All right, so as x is increasing, y is decreasing. This is going to be called a negative correlation. If I was going to try to have a line that was pretty close to all those points, you could see just like a downward line having a negative slope, we're going to say that these sets of data have a negative correlation. And you might be wondering, well, what's this third graph for? Well, sometimes you're going to have points that are all over the place. Okay? You may not be able to think, what kind of a line could possibly go through all those? And when you don't see that there really is any relationship between the x and the y, we say that they are relatively no correlation. Sorry, it's hard for me to write and talk sometimes. So points that where the x and y have no relationship really, they are relatively having no correlation at all. So why don't we look at some real life data. I've already plotted the points for you. I have two scatter graphs right now. And as you can see, the data in this one actually looks like it's going upward, and the data in this one looks like it's going downward. So let's look to see what it's actually talking about. The first one is comparing the hours of studying to test scores. And I can look at it and I can see, oh, it looks like it has a positive correlation. So what does that really mean? Well, if it has a positive correlation between the hours of studying and the test scores, then that means that as the hours increase, the test scores increase as well. And I think that for the most part you would agree with that from your own experiences, that the more hours you study, typically the higher test score you're going to get. Looking at this other one, it's comparing the hours of watching TV compared to test scores. And as the hours are smaller, the test score looks like it's higher. But as a student might watch more and more TV, it looks like their test score is going down. And this is going to be a negative correlation. Okay, and it looks like as the hours watching TV increase, the test scores decrease. And you may have had an experience like this where maybe one week you watched so much TV that you made no time to study, and it may have been reflected on that test score. Not all the time, but for this data, that's kind of what it appears to have happened. So we're going to look at a new set of data that has not been put on a scatter plot yet. What this data is showing is 5 different fish, and it's comparing the length of the fish to the speed of the fish as they swim in the water. So what I'd like us to do first is to create a scatter plot with this data. And what we're going to assume is that because we have length for our x's and the speed for our y's, that we can plot these just like they're ordered pairs. So the first one I'm going to plot is 38 up to 15. So it's around right here. The next one is 20 all the way up to 48. And the next one is 22 all the way up to 90. Whew, that's high. The next point would be 26 all the way up to 100. And the last point is 27 all the way up to 98. So this, I don't know, it kind of looks a little confusing, doesn't it? Because I have this one point down here that is kind of not reflecting what the rest is having happen, because it looks like as the length is smaller, that the speed is smaller. Okay, and then as the length gets bigger, the speed looks like it gets bigger, except for this one fish down here. Now, does that mean that there's not really a tendency for this data? Well, I think that since 4 of them do kind of fit the mold of as the length of a fish getting bigger and the speed of the fish getting bigger, I think that we can assume that this does have a positive correlation. What this point would be called an outlier. And that kind of is what you might find with data, that sometimes you might just have one piece of data that just doesn't fit, but everything else fits so well. But I think that we can assume that it does look like it has a positive correlation, even though this one point is kind of not reflecting that. So we're going to do one more set of data, and this time it doesn't tell us what the data is actually reflecting. We're just given the data, and maybe we can make some assumptions about this data, and by the end we're going to actually learn how to draw a fit line, a line of fit that will be very close to the data that we have. So I have a set of data, 1, 2, 3, 4, 5, 6, and 8 for my x's, and then my set of data for y's are 3, 5, 8, 9, 11, 12, and 14. So the first thing I want to do is create a scatter plot. So I'm going to assume that I can graph these as ordered pairs. So I'm going to graph 1, 3, 2, 5, 3, 8, 4, 9, 5, 11, 6, 12, and 8, 14. I think it's safe to say this time that it definitely does reflect a positive correlation. Unlike the time before, sometimes data can be kind of messy in the real world, and you may not know from the limited amount of data that you have if it really is reflecting a specific type of correlation. But in this case, it does look like it is a positive correlation. I think that you would agree with me. So we're going to write that down, that it has a positive correlation. Our next step, like I was talking about, was to try to draw a line of fit. And what this is, we're going to try to draw a line in between the data that is kind of closest to all the points. And when you do this, you want to try to draw a line that has half of the points above the line and half of the points below the line. So let's see here. Looks pretty good right there. So again, this is called a line of fit, and obviously these points are not on the line. It looks like I do have one point that's on the line there and possibly a second point. So what we're going to do now is try to write an equation using 2 points that are on the line. Now if you draw the line and there are no points on it, try to pick some points that you can see that the line passes through. Like I could see that this line looks like it passes through 1, 4. So if I wanted to, I could use that point. And there's several others that you can look for. So maybe I'm going to do that. I'm just going to pick 2 other points. I could have chosen some in my data set, but I'm going to choose 1, 4 as one of my points. And I'm going to choose, that looks like 7, 14 as my second point. And what we're going to do is we're going to try to write the equation of this line, and that equation is going to be a very good representation of all of the data points. Obviously, they're not all going to fit into that equation perfectly, but again, it's just going to be a very good representation. So to start, what we need to do is first find the slope. If I have my 2 points, I'm going to use my slope formula, y2 minus y1 divided by x2 minus x1. So that's going to be 14 minus 4 divided by 7 minus 1. I have 10 over 6, and that can be reduced to 5/3. So I found my slope, and if you recall, using the slope-intercept form, y equals mx plus b, I can choose one of my points, and I can fill in my slope to find the y-intercept. So I'm going to choose this smaller point, 1, 4, to plug in. So my y is 4, my slope is 5/3. My x-coordinate is 1, and I'm going to add the b. So I have 4 is equal to 5/3 b, or plus b. When I subtract 5/3 on both sides, I have 4 minus 5/3 is equal to b. I need to think of a common denominator, so I'm going to actually change this 4 to have the denominator of 3, so I'm going to multiply 3 on top as well, so that turns into 12/3 minus 5/3. And my b ends up being 7/3. So when I write my formula in slope-intercept form, I'm going to have y is equal to the slope, which is 5/3, times x, plus my b is 7/3. That means it's crossing the y-axis at 7/3. So just over 2. And I have successfully written an equation for the line of fit, this red line, okay, which is a good representation of all of that data. Now, a lot of this may have been confusing for you guys. We're going to look at a lot more examples in class, but I think that the most important thing that I want you to grasp from this lesson is what we did from the beginning. That if you're looking at a set of data on a scatter plot, can you tell if it has a positive correlation as the y's increase and the x increases? Or does it have a negative correlation? Or does there appear to be no correlation at all? And so come with any questions you might have to class tomorrow.